Time travel, black holes, and GPS. What do they all have in common? The answer would be Einstein's theory of relativity. It's one of the most groundbreaking ideas in modern science. And today, we're breaking it down to see how it affects our lives and our future. Hey, it's Ian, and welcome to another Science Done Right. For centuries, scientists believed that space and time were absolute, fixed, and unchanging. According to Isaac Newton's classical mechanics, time ticked at the same rate everywhere, and space was a rigid stage where the universe played out its events. But as we began observing the universe more closely, cracks started forming in Newton's theories. One major problem was the speed of light. According to classical physics, if we were traveling in a car at 100 kilometers per hour and throw a ball at it forward at 10 kilometers per hour, then the ball's total speed would be 110 kilometers per hour. But when scientists applied this logic to light, it did not work. No matter how fast you were moving, light always traveled at the same speed, which is approximately 299,792,458 meters per second, or about 186,000 miles per second. But then, it all changed when Albert Einstein came in. Albert Einstein wasn't just your ordinary scientist. He was a revolutionary thinker. Born in 1879 in Germany, he developed an early curiosity for mathematics and physics. At 26, while working as a patent clerk, he published his special theory of relativity in 1905. 10 years later, he expanded on it with general relativity. This wasn't just another scientific theory. It was a complete overhaul of our understanding of space, time, and gravity. So let's get to the whole shebang. How does relativity work? First, we have to discuss the two types of relativity, the special relativity and general relativity. Einstein's special relativity is built on two simple postulates. Number one, the law of physics are the same for all non-accelerating observers. Number two, the speed of light in a vacuum is always constant, regardless of the observer's motion. These two ideas led to mind-blowing consequences. First one is time dilation. The faster you move, the slower time passes for you relative to someone stationary. For example, astronauts aboard the International Space Station experience time a fraction of a second slower than people on Earth. Second one is length contraction. At high speeds, objects shrink along the direction of motion. For example, if a spaceship were moving at 99% of the speed of light, it would appear half its normal length to an outside observer. And lastly, the relativity of simultaneity, which is two events that appear simultaneous to one observer might happen at different times to another observer moving at a different speed. So let's take for example the twin paradox. If one twin stays on Earth while the other flies near the speed of light, the traveling twin will return younger than their sibling. Special relativity was just the beginning. In 1915, Einstein introduced general relativity, a new way to understand gravity. Instead of being a force, gravity is actually the curvature of space-time caused by mass. Massive objects like the sun bend space-time, and smaller objects like planets move along these curves. This was proven in 1919 when scientists observed light bending around the sun during a solar eclipse. Another wild consequence? Gravitational time dilation. The stronger the gravity, the slower time moves. This has been confirmed by experiments placing precise atomic clocks at different altitudes, and they tick at different rates. This begs the question, so what? How does relativity actually benefit humans? Well, number one, GPS wouldn't work without it. Do you think relativity is just abstract science? Well, you have to think again. Every time you use GPS, you're relying on Einstein's equations. GPS satellites orbit Earth at high speeds and in weaker gravity, meaning their onboard clocks tick 38 microseconds faster per day than clocks on Earth. If we didn't apply relativity corrections, GPS would become useless in just a matter of days. Number 2. Nuclear energy and weapons. Einstein's equations E equals mc squared shows that mass and energy are interchangeable. This led to two major developments. Nuclear plants, which generate electricity by converting tiny amounts of mass into massive amounts of energy. Number 2, nuclear weapons, which unleash devastating energy using the same principle. Without relativity, we wouldn't have nuclear medicine, nuclear submarines, or atomic energy. And lastly, black holes and gravitational waves. General relativity predicted black holes, objects so massive that nothing, not even light, can escape their gravitational pull. In 2019, the first ever image of a black hole was captured, proving Einstein right once again. And in 2015, scientists detected gravitational waves, ripples in space-time caused by massive cosmic events. Einstein predicted them a century later. Okay, so there's that. But what will relativity potentially do in the future? If we ever want to reach other star systems, we'll need to master relativity. Future spacecraft might use light-speed travel or even warp drives based on space-time warping principles. Second, understanding time dilation could help astronauts on long missions. See, they might age slower than those on Earth, making deep space travel more viable. And lastly, Einstein's theories may also play a role in the future of quantum computing, AI-driven space exploration, and even better models of the universe's structure. At the end of the day, relativity isn't just a theory, it's reality. From the GPS in your phone to the future of space travel, Einstein's work continues to shape our world. Stay curious and remember, time is relative. I hope you thoroughly understood the concept of relativity and its impacts in this video. Goodbye and take care, and remember to stay curious, stay learning, and stay on the right side. Peace out.